Any formula that we have ever that comes with different shapes is all going to be derived from something with triangles. All right, so this is the start of chapter 5. It's, I would assume, going to be 2 sections, if I remember correctly. So essentially there's 3 things. We've already talked about angle bisectors, so there's not really a new definition of that. Even perpendicular bisector, we've done the word perpendicular. You know that makes a right angle. Bisector you already know, so you can kind of piece that together. The only word that wouldn't be familiar yet is the mid-segment thing, which is what we're starting with. But it's a pretty easy concept, guys. And what they are is pretty easy in terms of definition. And it's actually something that's going to be in multiple chapters. Like that word won't change. You'll see it in a few different chapters. All right? But everything in here is going to relate into triangles somehow. Okay? The first thing is the new definition. This is the one that we haven't even talked about. All right, mid-segment. Mid-segment is combining 2 words. It's combining midpoint and segment together. You're putting those 2 things together into one word because the words are what make up the definition. Okay, so mid-segment is simply just a segment that connects 2 midpoints. That's it. And for what we're dealing with today, it's triangles. So that's why it'll say at the end of it, it says, you know, of the sides of the triangles. But I have this written out specifically for triangles. All right, but this could apply to pretty much any kind of polygon that we're dealing with. Like the next place you guys will see is when we get into trapezoids. Okay, you'll often see them in there. But anytime you connect 2 midpoints, all right, you can technically classify it as a midsegment. So, we'll see what it looks like. That'd be it. All right, so it's basically taking a triangle, and inside of it, it's dealing with a segment. Because the main thing, what's happening in this chapter, guys, is we're going to start working with segments inside triangles. This is just the first one we run into. Okay, so all we've dealt with in the past before this would be sides of an actual triangle, so now we're moving to the inside and dealing with the properties of these. Okay, so, and when you look for these, the way you'll identify it is they'll either flat out tell you, hey, this is a midpoint, okay, or you'll see the congruent marks here and here to identify the fact that that is in the middle. All right, so either way you see it, like it could actually say, if these were points A and B, and I didn't have those congruent marks, I might say point A is the midpoint of that side and point B is the midpoint of that one. So that would identify that since this segment is connecting to midpoints, it would be technically a mid-segment. All right, and identifications like that are good because you're going to have a theorem that kind of comes off of this that you need to know. It's going to be how you do the problems today that involve it. In terms of lengths and maybe another property to it. So just look for those identification things, like either the congruent marks or just in the directions basically saying, hey, this is the midpoint. All right? So the theorem. Okay, this is again going to be the way you're dealing with the problem. It tells you how to set these problems up. It's a real, pretty easy concept. Okay, there's 2 things. If you've got a triangle, you've got a mid-segment. And they've identified this one, segment DE is the mid-segment of that triangle. So I know that D is the midpoint, E is the midpoint. All right, which would in turn allow me to mark the things congruent that they have. The 2 properties that come with this theorem are going to be how the mid-segment and then the side directly below it, or directly like next to it, below it, it could be sideways, but right in this case it's below it. It's how these 2 relate to each other. One thing's already marked, like these little arrows mean what? What do they mean again? Parallel. So one property is going to be that they're parallel, which means that since those are parallel, that means I could go into doing anything I did with transversals, okay? Like with parallel lines and transversals, right? We had those angles being congruent. These are corresponding angles, which ties into this one, because these 2 right there are corresponding angles, or these. Okay? So the properties, like one of the properties is the parallel, the angles, those corresponding angles, right, in transversals, that just kind of stems from it. Okay, you're allowed to add that to it because we've already done those properties. So this still ties all the way back into chapter 3. The other thing is going to be the length of them, how they relate to each other. When something's in the middle, like you should automatically think it cuts something in half. And that's an easy way to kind of remember this theorem. Right? Mid-segment's always half of the side that it's parallel to. So whichever ones are parallel, and it'll be obvious, guys. I mean, if you know the definition of what parallel is in terms of lines that don't intersect, I say, look, the mid-segment's always half of the side it's parallel to. You should be able to match them up easily. Yeah. That would be the whole then part. So the actual theorem goes, if all this happens, then this. All right, that's why I stopped with the then part. So it would be things like if you need to see numbers up there, it would be the whole idea that if you know this is 18, that would be 9. Okay, and this is an easy concept, and these things are drawn in there because, I mean, it's real quick to find half of something. Or even set up equations that involve that. Okay, so, I go past this. Okay, so this would be one type of question. And I'll do two. Like, you'll do problems where they're going to give you actual numbers, like flat out, here's the side length, here's the length of a mid-segment, and they'll ask you to find other segment lengths. And then the other type would be solving for x, like setting up equations based on where these are at, like using the actual theorem to set these up. So this question just asked me to find RT, right, which is this one, RT, and it's asking me to find this one right here. Guess what they should be? UW is 6. Why is it 6? It's half of 12, right? So these two right here are the parallel. All right, and the reason, again, the whole reason I can do that is because that's a midpoint because these two are congruent. That's a midpoint because these two are congruent. That makes that a mid-segment, which means I can then do all that. Okay? All right, so that's 6. What about this one? 16. Again, because RT and BW are parallel to each other, BW is a mid-segment, you just double it. Multiply by 2. Okay? Not that difficult a thing to do. It's just an identification thing. You can identify a mid-segment. You're going to make your life a lot easier in terms of figuring out size. Okay? Can I go past this, guys? Alright. See the other one. Then I'm going to have you guys do some problems on your own. Okay, the workbook. Alright, so this would be the other type where, like for this one, they would probably identify that like Z, X, and Y are midpoints of those sides. So like Z is the midpoint of OM, X is the midpoint of MN, and Y is the midpoint of OM. Like that would be given to you in the directions. Okay? So assuming that I'm telling you those are all the midpoints, and the question is asking you to find the length of WZ and the length of MO, you should be able to do it because you would know that that line right there is a mid-segment, like ZY is a mid-segment, ZX and XY. Those are all mid-segments. So they're connected mid. Okay, which means all I have to do is identify which ones are half of each other, which sides match up and so on. All right, so if I look at the top one, the first one there, it's giving me YZ and MN. So if I was looking at it, probably the first thing I would do is make sure that these two are the parallel ones, which are YZ and MN the parallel ones? Yeah, because they're going the same. Okay? And then I got, that's 3x plus 1. This whole thing is 10x minus 6. What do you think I would do to solve this out? I can do that. That's fine. The thing you got to remember is just kind of identify, make sure you realize which one's the bigger segment, guys. The bigger one is always going to have a 1/2 with it. Or in this case, if you do it like you identify, look, that's the smaller one. I can always multiply that by 2 to give you, like, the equal amount. All right, one has to be altered somehow. You can't just set an equal to either. Not if you're dealing with the entire length of that side. If I was dealing with like MX, I can set those equal to each other. Yes.
So you can either cut the bigger one in half or multiply the little one by 2. Yeah.
Usually it's easier to multiply by 2. Because sometimes, if you do a half, you'd be left with like a decimal or something, fraction, which is usually people get more frustrated with that than multiplying by 2. All right, so if I solve this out, I get what? 10x minus 6 equals 2x plus 2. What would I do after that? So that gives me 4x equals how much? 8 2x's. Is that my answer? No. What do I have to do to get my actual answer? Plug it in. So you'll get, if I plug the 2 into yz, you'll get how much? Okay. All right, now the second one there. Go through the whole checks again. All right, so we're still dealing with the same idea that these are all mid-segments. So that means all I got to do is match up the ones that are parallel. Okay, so like this one here, you got XY, and you got MO. Again, are these the two that are parallel to each other? Are they? Yeah. All right, so if I'm doing this, I've got x minus 1 there, 3x minus 7 there. So again, how would I probably set this up? You guys agree? Which one, right? Okay, so the 2, then when you multiply by 2, make sure it's always with the smaller one. All right? So there we go. We got, so if I distribute, I got 2x minus 2, it's 3x minus 7. So if I move everything accordingly like I should get x equals how much?
9.
5 or 9?
9.
Which one?
9. 5 on that.
Yeah, I think 5. Okay. And then again, that's not my answer, right? I would take this now, plug it into the 3x minus 7, because that's what I get. So if I take 5 and plug it into 3x minus 7, you get how much? Okay? With perpendicular bisectors and angle bisectors. Both of the theorems are going to be kind of similar. They're just drawn with different things, so they'll look a little different, but the whole idea behind them is essentially the same. With what we're working with now, when you create a perpendicular bisector and an angle bisector, we're going to focus on what kind of congruent segments can be created from them. First thing, just to kind of remind you, right? Perpendicular bisector would be anything that will bisect a segment and at the same time create a right angle. So that's the whole name of it. Perpendicular means you're creating a right angle, bisect means you cut it in half. Okay? So if I was to say, look, like in that one, if I had the picture drawn out, and say I didn't have anything marked, I just had CP and AB crossing, and I said CP is a perpendicular bisector of AB. Like me stating this right here would allow you to go in the picture and put these congruent marks in there and the right angle right there. Okay, because that's what, again, it means. Bisect means it cuts it in half, right? Creates 2 equal segments, just like always. Like bisect always means, perpendicular always means makes a right angle. So the definition for this one, like in terms of everything that's up there, isn't really extremely new. These are 2 words that you've used before. I don't think we ever dealt with it drawn out specifically. Okay, so in that case, it is a little different. All right, but the essence of it, guys, is old stuff. Okay, things that we've dealt with before. Now, the theorem that you guys are going to have that comes off of this deals with points that are on the perpendicular bisector, like the point C, okay, or any point that's on it. Like C is the only one that's actually drawn on there, so that's the only one I'm mentioning right now. And the theorem is going to basically show you how this point relates to the endpoints of the segment that's being bisected. And it'll go for any point that's on it. All right, it could be a point down here, up off of it, down here, wherever. Okay. Can I go past this to the actual theorem, I guess? Do we need me to sit here for a second? All right. So the actual theorem goes, if you have a perpendicular bisector, okay? So if you have a perpendicular bisector, then any point that's on that line is equal distant to the endpoints of that segment being bisected. It's kind of a mouthful to say, and it kind of confuses people. But the whole essence is saying, if that's a perpendicular bisector, the distance from P to A is the same as it is from P to B. If I were to fill in the blanks for the things I have there, like AM and MB obviously would be the same because that's the bisecting part. But the actual theorem deals with this part. So this is the if, this is your hypothesis, this is your conclusion. And then we'll go for any point that's on there. If I take a point like above P or below it or wherever, it wouldn't matter where, the distance to the endpoints is always going to be the same. Okay, so that's basically what the theorem says. If you got a perpendicular bisector, any point you pick on that line, even if it doesn't look like it extends beyond it, like if it's down here, if they extend it down this way, any point that's on this line is going to create two equal segments to the endpoints. Okay? So that's pretty much it. That's all it says. And right now, we're not really transferring it. Like, we're creating triangles. Like, if you look at it, yeah, there's two triangles created there. Okay? So we could technically work with them. They're isosceles triangles and so on, so we could deal with them. But it's going to tie into more triangle stuff tomorrow. Okay, we're going to take these and basically put them inside triangles tomorrow. But this whole theorem is never going to change. Even with the stuff tomorrow, it's going to be the same theorem. We're going to use the same. All right. Now, this theorem and even the angle bisector one are going to have converses as well. I think with this, I have an example first with how you're going to deal with it flat out as the theorem, as it says up there. Then there's the converse. These problems are actually going to be very quick. There aren't really ever too many tricks with these. Because the whole practice of this is simply just seeing if you can recognize when a perpendicular bisector exists and seeing if you can recognize which segments are congruent. All right? I got the converse first. Let me come back in a second. Show you. I don't have any. Before I do that, like just to show you an example of probably something you might see. They might have like a segment drawn out, and we'll have a line going down there. Okay, that's A. All right, and it might say something like line BD. The perpendicular bisector AC. And it might say something like maybe we'll do AC equals, I don't know, give me a number. How long is AC? What?
96.
Sure. How much?
96.
96? So we'll say AC is 4, and then we'll do like DC is, you want to do 96? I can't do Like this might be all the stuff that's given to you. You'll have a diagram, you have this given, and they'll say something like, find AB, BC, and AD. Like it'll ask you to find those. And basically what it's trying to get you to do is recognize that it's a perpendicular bisector. So it's creating two equal segments. All right, so if you know AC from here to here is 4, these two should both be how much? 2. All right, which gives you those two answers. And then it also gets you to kind of recognize, hey, it's a perpendicular bisector. Any point that's on this line that's bisecting it, if I connect lines to the endpoints, they're always going to be equal. So if I knew this one's 96, this one over here has to be the same length. That's what the theorem says. So there's not work per se, like you're not doing that. It's mostly a recognition thing. You need to be able to identify which segments are congruent. Like that would be an entire problem, okay? So they should be quick, as long as you recognize which parts are equal. All right, now the converse of this would be like everything that's up there right now. The converse would just basically say that if you've got a point equidistant to the endpoints of a segment, such as drawn right there, if I drew the perpendicular bisector of this segment, it would have to pass through point P. It's kind of what the converse says. All right? So anytime you've got a point that is equal distant to the sides, or to the endpoint, sorry. If I were to go in there and draw the perpendicular bisector, it would have to pass through that point. Okay? That's kind of what it says. The drawings should look similar between, like diagram-wise, between the original theorem and the converse. The difference is the order, right? Because converse, again, means you flip-flop hypothesis and conclusion. It's just the theorem just in reverse. Now, the problems you'll see with these are going to be more like yes or no kind of problems, where they'll give you a point, and then they'll have like a picture, they'll give you some point, they'll just say, is this point on the perpendicular bisector? All right? You're just going to have to look for things like, to see if it's actually a perpendicular bisector, like a right angle with the segment split, or you'll have to see these two segments being marked congruent, that kind of thing. So the type of problem, but again, the problems are going to be quick. They should be. So like these would be two types of problems right there, or two problems. This would be used in the converse, where it's saying, hey, look at the picture, all right, and see if there's enough information to determine if that line right there is the perpendicular bisector, or if C is on the perpendicular bisector. Okay? So you're either looking for it actually to be marked as a perpendicular bisector, so right angle and it's split, or you're going to want to see the point being equal distance to the two ends. All right, so on the one over here on the left, you guys think that point is on the perpendicular bisector of AB?
No.
No, why not?
And A and B, or AC and BB are not equal.
Yeah, they could be, but they don't give me any information here, so I can't
Don't look
determine
like
anything. Okay? Does it look longer?
Yeah.
Yeah, it looks longer. But that just could be because they can't draw it. The actual answer would be I can't do that. Right? Maybe your eyes.
If they explain the reason.
Well, that would be explaining. There's not enough information. I'll not. I wrote it down in my head. And then this one over here, same question. It's basically saying, look, if I extend this line out, all right, is it going to pass through C?
Yes.
Why?
Because
It is a yes answer, but why?
They're both 4 and 4, and
Yeah.
then 8 and 8.
Yeah, the 8 and 8 tells you. Like this point is the same distance to the endpoint. That's all I got to say. Okay? It's same distance to the endpoints. It has to be on the perpendicular bisector. That's what the converse says. So, but these problems are going to be yes or no answers, and it'll be a quick explanation. Okay? So again, they're quick problems. They should be. All right? Now, for the angle bisector. Okay, so angle bisector, again, we've dealt with that definition. I'm not going to rewrite out that definition. Angle bisector is you bisect an angle, split it. All right, here's how this theorem goes. All right, and this is if then with the picture. All right, and the way the pictures are marked is extremely important in this case. All right, so basically what it's saying is that if you've got a ray that bisects an angle, like rays can bisect angles, and you pick a point somewhere on that angle bisector. In this case, they got F. That's just the point they've used. That point is halfway in between the two sides. So that if I were to draw, right, if I were to draw the length from this point to the side, it's going to be equal to each other, right? So that they're going to be congruent, which they have marked over here. Now, what this is actually doing, guys, this is doing the distance from a point to a line. When you do the distance from a point to a line, you have to create a right angle. That right angle being right there is extremely important here. On the problems when you deal with these, if that right angle is not there, they're not doing the exact distance from this point to a line. Like if I just saw something drawn, if I said, oh, that's bisected, and I say, okay, here's point A, I just draw a line going that way, and I say that's 3, that's not the exact distance, or I haven't specified it is. That could just be a random segment I drew over there that's a length of 3. If I want the distance from this point over to that line, you have to create a right angle. That's the shortest distance, which is what you're trying to find. Okay, so that the way these are marked is extremely important for what the problems are going to be. All right, but it's basically saying if it's on the angle bisector, it's equal distance to the side. Any point that's on here. If I pick a point here, and draw on all those things, those two are going to be equal. All right, doesn't matter where it's at. There. Okay, so it's going to be similar types of problems. All right, I'll worry about that. Okay, so this would be a kind of problem you would see. Just like the perpendicular bisector thing, where they say, look, I've kind of got things marked off. All I want to know is, can this point be on the angle bisector? If I drew a line that was bisecting this angle, okay, and I'm just going to draw it through it just because I can right now. Doesn't mean it is. But if I drew a line that's bisecting that angle, all right, would that line pass through that point? That's pretty much what the wording says up there. Let me read the wording I agree. Now, what you got to remember, like I said, the stuff that was marked off has to match up exactly. Everything that was on this screen, the way all that is marked, right, on this side right here, has to exist in the new one. If something's missing, or if they marked it different or anything, then your answer has to be not enough information. Okay? So, all right, so this one on the left here. If I drew that line out, if I drew that angle bisector, is there enough information for me to decide if that point's going to pass through? Yes or no?
Yes. No.
We got both, yes and no. The right answer is no. Or not enough information. Main reason is it's not marked correctly. That what you need to see, you have to see it. You have to see these two being congruent, which they are. Okay? But again, remember, this point is to be halfway in between. You have to do the actual distance. I would need to see right angles there, which I don't. That's the biggest issue. I can't determine if that's the actual distance from that point P to the two sides. Okay? So that one's a no. What about the one over here?
Yeah.
Yes? I don't know.
No.
Actually, if you think yes, you go, no, I don't know. You say
No.
no?
It's no.
Why?
Two right angles.
Yeah, I don't have a right angle down here. I don't know if this is drawn like this, or whatever. All I know is that the first line, that measures the distance from that point to this side. This one, maybe not. It might be. I mean, it might be. They didn't show enough there. Okay? If it had the right angle there, it'd be a yes. That's the only thing missing. That one little right angle. Okay? The biggest thing with these is make sure it matches up exactly like the picture. Okay?